Hello everyone again and welcome to my channel. Excited to be back again and actually talk to you about an interesting subject which is more related to quantum chemistry. Now, if we throw back to our understanding of a typical potential energy surface of a diatomic molecule shown below here, then what we see is that first of all, our diatomic molecule, which consists of chlorine and hydrogen with a bond in between, starts off first with a high energy due to the great repulsive force, and then as we get closer to this particular region, which is our value 4r, which is the internuclear distance r, then we approach an equilibrium here at room temperature, which is represented as r naught here, where the bond distance is actually stabilized in there. And then as you get closer to other regions here, there is an interesting plot where we go from a Hooke's law curve to a bond breaking as a result of the stretch of the covalent bond in here, which is in this particular region, where this is the stretch that leads to the breakage of our bond, and in this particular region here, which is a high energy due to the great repulsive force between the two nuclei and between the electrons in there. Now, take note that the potential energy surface relates to the geometry of the molecule, which is given by its nuclear coordinates to the molecule's potential energy. And in this particular part, therefore, our goal in this particular video is to be able to find how is the harmonic oscillator related to the molecular vibration of our bond in here. Now, let's look at a typical case of a Hooke spring, which is expressed as this formula or curve, over here, where this curve over here, where we have our middle section, which is the symmetrical point to be x equals 0, or I would say r equals 0, where r is actually our distance between our two nuclei or two atoms in here, and then there is no form of actual translation in our Hooke spring in there, and the formula in here is actually expressed as Vx equals to 1 over 2 multiplied by our constant, which is the force constant, multiplied by the x. Now, this is similar to a quadratic equation, and this quadratic equation tells us that any translation in the x, we actually change our x coordinates in here to be x minus a particular value if you're moving to the right, or x plus a value if you're moving to the left of this particular curve over here. So in this particular case, where this is representing our harmonic oscillator, and this particular region is actually relating this to our molecular vibration, which is between these two nuclei, where this bond is actually compressing and stretching in there. What we see is that we need to take into consideration as well the movement of this whole mass over here, which is represented as m, to be moving both in the x positive and x negative. In this part here, this shows a free particle state, and in this other part here, we are taking into consideration a diatomic molecule. So in this particular part, from here we can then go into this particular part, which shows a plot where we see the similarities and yet differences between our harmonic oscillator here and a regular bond, which later breaks off in here, where this represents a diatomic molecule which has one atom with m1 mass and another atom here with m2 mass, and then you have a distance which is between the two nuclei in here, and then where this particular curve, which is painted in black here or written in black, is actually translated to a specific number for our x, where you're moving to the right. So in this part, there's a translation going from this to that over there, which is expressed as VR equals to 1 over 2 x into bracket r, where r is the internuclear distance, and then you're translating it r naught unit to the right. And in here, this r naught actually represents our translation unit to the right, and this physically represents the equilibrium bond distance, and this is actually most stable state of the bond at room temperature, which is R naught over here. However, for our K, we actually know this to be our force constant, and this our force constant, it depends on the molecule, and in this particular part, the stronger the bond, the bigger the value of K, and the more compression actually results in this particular process over there. Now, focusing on one dimension, the reduction of a two-body problem, which is represented as this, where we see mass 1 and mass 2. In between here, we have a bond that is represented as a string which performs a vibration in here, and later we'll talk about how this bond will break off, which is actually satisfying our curve which we talked about in here. And we have a distance between mass 1 and mass 2, which is the nuclear distance or internuclear distance, represented as r. And in here we have the relative positions of our atoms in this molecule, where it's positioned in x1 for mass 1 and x2 for our mass 2 in there. So this is actually reduced into two one-body problem, which requires first the consideration of two masses to only move along the x-axis as shown here, and then secondly we also take into account the classical kinetics of this two particle system, which is represented as this formula over here, where we have mass 1 which has its own velocity moving in the x-axis here, v1 squared, and this is the kinetic energy for mass 1 and this is the kinetic energy for mass 2, and this total represents the kinetic energy of this whole molecule in, I would say, one-dimensional space. Now, where x dot is actually taking into account the velocity of our relative atoms in here in this our molecule, which is equal to dx over dt, and dx over dt is also equal to v. There we can substitute this for v1 and substitute this for v2, and then this will actually produce this formula over here, where x dot here represents the velocity of our atom m1, and x2, which is small x2, is actually equal to the velocity of our mass 2 over there. So take note that in here we're also focusing on the translational motion of the center of mass, which is represented as big letter X Sm, and we're also taking into account the vibrational motion with respect to the distance between the nuclei over there. So take into consideration our center of mass of this molecule. Now in this part, then we actually notice the formula to be equal to this. Now in this part here, when we solve our formula by taking into consideration r to be equal to the subtraction of x1 from x2 in this particular case, then what we therefore realize is that expressing x1 and x2 in terms of big X, which is the center of mass, will actually yield. So as a result of that, by multiplying 1 and 2 by d over dx, putting this into this equation in here, which is, I would say, equation 1, then what we produce as a result of that is this particular formula, which is the total energy or kinetic energy of this body in here. Now, this total kinetic energy takes into account the mass 1 and mass 2 and its center of mass, velocity, and you're adding it with the reduced mass in here. So in here we have the reduced mass, where this particular formula actually is the reduced mass, and that will actually make us to see first that, hey, this here actually represents the translational kinetic energy motion for the center of mass, while this formula part over here represents our vibrational kinetic energy of the diatomic system. So therefore, the total Hamiltonian is expressed as the combination of the total kinetic energy, which is this, and that of the potential energy, which is translated from the Hooke's law. So from the Hooke's law, where we talked about it over there, then by considering both the potential energy over there and the kinetic energy, which is what we got over here, we arrive at this formula, which is the Hamiltonian operator for a two-body problem in one dimension, where we see the relationship between our translational motion and our vibration motion, which is actually linked also to understanding how we can see the relationship between this particular segment, which depends on the center of mass, and this other segment here, which depends on the variable x, which is the internuclear distance. So as a result of that, what we notice is that this formula can also be separated in here into the translational motion, Hamiltonian, and this other segment over here, which is the Hamiltonian for our vibration over there. The interpretation of the harmonic oscillator wave function to probability on our previous video reveals that first, if you have this particular wave function, which is actually now a probability, we notice that in these regions we have more kinetic energy. That is, the molecules, they tend to move faster in this region, and in this particular regions over here and there, we have particle actually spending more time for they actually slow down during vibration. That is, when they actually change direction from going this way to that way, and in here they change direction going from this way to that way. So this to and fro movement is kind of similar to what we have in terms of this particular swinging ball, where on this region here we have the highest potential energy and a low kinetic energy, and the same thing follows in here with a high potential energy and a low kinetic energy. And as you move towards this particular center regions over here, or this over there, what we realize is that we have more kinetic energy in this particular part over there, where the maximum is actually at this region over there, and here we have a low potential energy over there. So that's about it for this particular video. Hope you're able to understand the relationship between the harmonic oscillator and the vibrations of a molecule, and how that translates into the Hamiltonian operator in terms of containing both our translational Hamiltonian and the vibrational Hamiltonian that contains both the center of mass and the reduced mass. So all the same, thanks for watching. Please hit the comment down below, let me hear your thoughts about this subject, and talk to you all later. Be smart.